We spend our entire days tapping, swiping, and clicking away. But have you ever actually stopped to think about what happens in that tiny split second after you click something? Well, we're about to follow one single command on this incredible high-speed journey right through the heart of your computer. Let's get into it. I mean, really think about it. You click to open a program, and it just appears. It feels instant, like magic. But that one simple action kicks off this perfectly coordinated, high-speed ballet of electronic signals. So where do they all go? And what are they actually doing? So that's what we're going to do here. We are going to trace that one click from your finger, deep into the brain of your machine, and all the way back out to your screen. It's really a story of unbelievable speed, pure logic, and just some truly brilliant design. All right, first up, let's just look at the basic layout of a computer. And what's really wild is that the fundamental blueprint we still use today is a design that's actually over 75 years old. Yep, you heard that right. This amazing design, it's called the von Neumann architecture, and it is the foundation for pretty much everything, from these massive supercomputers to the smartphone that's sitting in your pocket. The genius of it is just how simple and logical the whole flow is. And here it is, that basic flow. Your click, that's the input. The computer then processes that command. It uses storage to either grab or save info. And finally, it shows you the result as output. Input, processing, storage, output. Seriously, every single thing you do on a computer follows this exact same path. Okay, so now we're at the most critical stop on our journey, the processing stage. This is where the real heavy lifting happens, inside a tiny component called the central processing unit, or as you probably know it, the CPU. Just think of the CPU as the tireless, hyper-efficient CEO of the whole operation. It takes your click, it figures out exactly what you want, and then it tells all the other parts of the computer what to do to make it happen. And it does it all pretty much instantly. And what's so fascinating is how the CPU divides up its work. First, you've got the control unit, which is kind of like a traffic cop, directing the flow of all the data. Then there's the arithmetic and logic unit, or ALU. That's the math whiz, the super fast calculator doing all the hard sums. And finally, you have registers, which are like a tiny, lightning-fast scratch pad for holding on to numbers the ALU is working on right that second. So we always hear about speed in gigahertz, or GHz. You can think of that like a car engine's RPM. It's how fast the parts are spinning. But that doesn't tell you how fast the car is actually going, does it? For that, you got to look at MIPS, or BIPS. That's millions or billions of instructions per second. So here's the bottom line. A high clock speed is great, but how efficiently the CPU uses each one of those ticks is what really gives it its power. All right, so our CPU is all revved up and ready to work, but where does it get the data from? And where does it put the results? Well, for that, it needs memory. And as we're about to see, the computer uses two totally different kinds. This workbench and warehouse analogy is just perfect for understanding the difference. Volatile memory, like the RAM in your computer, is your workbench. It's where you keep everything you're actively working on. It's fast, easy to get to, but, and this is the important part, when you turn the power off, poof, the workbench is cleared. Non-volatile memory, like your hard drive, well, that's the warehouse. It's for permanent, long-term storage, keeping all your files safe and sound, even when the computer is totally off. Okay, let's get a little more specific. RAM, or random access memory, that's the main workspace, that workbench we just talked about. But your computer also has something called ROM, which stands for read-only memory. The best way to think about ROM is as the computer's permanent, built-in instruction manual. It has the most basic startup instructions, telling the machine how to wake up. You can't change it, and it never forgets, which is exactly what you want for such a critical job. So, if RAM is the workbench, you might be wondering, where does cache fit in? Well, think of cache as a tool belt that the CPU wears. Instead of having to walk all the way back to the workbench for every little piece of data, the CPU keeps the tools and info it uses all the time right there for instant access. It's a simple idea that makes everything run way, way faster. And when we talk about how much data these storage areas can hold, the numbers get huge, and they get huge fast. We start with a kilobyte, which is just over 1,000 bytes. From there, we jump to megabytes, then gigabytes, and now it's pretty common to have terabytes. That's roughly 1 trillion bytes of information. Just wild. Okay, so let's recap. Our click has been processed, and the computer has found the data it needs in storage. But wait a second, how did the computer even get our click in the first place? And how does it show us the result? Well, that brings us to the computer's senses and its voice. It's input and output devices. Input devices are quite literally the computer's senses. It's how it perceives the world and us. This includes the obvious stuff, your keyboard and mouse, but also its eyes, like cameras and scanners, and its ears, like microphones and voice recognizers. And boy, have those senses evolved. I mean, early computers used things like punched cards, where every single piece of data had to be physically punched into a piece of paper. Now, a QR code reader on your phone can just glance at a little square and instantly pull up a massive website. It's an absolutely incredible leap in a pretty short amount of time. So, once all the work is done, the computer needs a way to tell us the result. This is its voice. The most common one is the monitor, of course, but it also includes printers for paper copies, speakers for sound, and really importantly, accessibility devices like braille readers that can provide output through touch. So the journey of our click inside this one computer is almost complete. But today, no computer is an island, right? They are all connected, all the time, forming these huge networks that basically power our world. And these connections aren't just a big jumbled mess. Networks are organized in specific patterns, or topologies, that define how all the data flows. For example, you have a star network, like you see in the top right, where everything connects to a central hub. Or you have a bus network on the bottom right, where all the devices are lined up along one single main cable. Each design has its own unique strengths and weaknesses. And here's really the key takeaway. All these concepts, the CPU, the memory, the I/O, the networking, they don't just apply to your big desktop computer. They're the fundamental building blocks of every single smart device we use, from our phones and watches to our smart refrigerators. We've turned everyday objects into tiny, powerful connected computers. So, when all these millions of smart devices are connected together over the internet, they form what we call the Internet of Things, or IoT. This means that single click doesn't just travel inside your one machine, it can connect you to a global network of processing power and information. I mean, just think about it. We've gone from computers built with vacuum tubes that filled entire rooms to devices with exponentially more power that literally fit on our wrists. The journey of that one click has become faster, smaller, and more connected than anyone could have ever imagined. Which leaves us with one last, really exciting question. Where does that journey go from here?